Hello, this is Jiawei Wang from the University of Tokyo. I'm excited to share our work on large language models as urban residents, an LLM engine framework for personal mobility generation. Urban mobility generation is about simulating the daily activities of individuals. And to do that effectively, we need models that can plan like humans. And this is exactly the advantage of LLM. First, the LLMs has the ability to understand the context and process nuanced information. Second, LLM have shown remarkable versatility in dealing with unseen tasks. The motivation behind our research is simple. How can we leverage the power of large language models to generate and simulate urban mobility behavior? In our research, we highlight three challenges. The first is how do we align the model with real-world data? The second is about effective generation challenges for reliable and meaningful activity generation. And the last is to explore the potential application of the LLM in the context of urban mobility. And so in this figure, our framework revolves around trade-off thought prompting to generate individual activities based on historical data. We guide the model step by step. First, we prompt the model to identify the person's daily pattern, then infer their motivations, and finally plan their daily activities. The first step is identify the activity pattern using the LLM. We begin by processing historical data and prompt the LLM to describe the daily pattern as an urban resident given a candidate persona. At this stage, we introduce multiple candidate personas, allowing the model to generate a variety of potential activity patterns. From there, we apply a self-consistency sampling to evaluate and select the most coherent output. Notably, we ask the LLM to score each candidate pattern. Since the model cannot evaluate an output on the fly, we devise a compressive scheme. In this approach, we prompt the LLM to act according to a given candidate persona and evaluate the likelihood of a specific daily plan. This plan could either belong to the target person or someone else. The LLM, following the most reliable pattern, shall assign a higher likelihood to the target person's activity and a lower likelihood to the plans from others. Next, we move to the generation phase by introducing a reasoning logic to derive activities from the motivation. We propose two schemes to infer the motivation here, depending on the data availability in real-world scenarios. The first motivation retrieval scheme is targeted at a situation when we have sparse data. Here, we prompt the LLM to infer the motivation behind each of the latest historical days and plan future activities according to the historical motivation. We call it evolving based on the prior that motivations are evolving from day to day. The second is called learning-based motivation retrieval. If we have enough long-term data, we can train a selector to identify the days from the historical data and then prompt the LLM to infer the motivation behind these days. Because in real-world applications, to simulate daily activities, the key information we have is only just the date. Here, we implement a compressive learning scheme. For each date, we generate a positive pair and multiple negative pairs. The objective is to train the selector to accurately identify the most similar historical dates to the target. Once we can find the most relevant date, we can prompt the LLM to infer the motivation behind the activities on this date. For our experiments, we use data from the Twitter and Foursquare APIs on the Tokyo area from January 2019 to December 2022. We use ChatGPT 3.5 Turbo in this study. We evaluate the model by comparing to the baseline studies using 4 key metrics, and we design 3 generation settings based on different pandemic periods. While our model may not always replicate spatial features, it did well in temporal dynamics. It also very competitive in spatial temporal metrics like DRD and STVD. We suggest that the strength of our model in these metrics comes from the ability to accurately replicate the motivation behind individual behaviors. Thanks to the LLM's deepest semantic understanding, we can capture not just the where, but the why of human behavior. In a later experiment, we design a responsive simulation test. We prompt the LLM engine by providing a specific scenario description, the pandemic period, to see what daily activities will be simulated. The daily activity frequency radar plots so that our framework can capture pandemic patterns more effectively than one of the baseline approach. We also check the activity distribution reproduced from our framework. The pandemic effect is well reproduced only by just injecting a prompt. This offers a promising approach for analyzing crowd behavior in urban areas across different situations. Let me finally sum up our contributions. We have built a novel framework that uses LLM for generating personal activity data, and we should introduce a self-consistency sampling method to align LLMs effectively with mobility data. Our techniques made the activity plans interpretable and actionable. And finally, we have shown how well this works with real-world mobility data. Thank you very much for your attention. And if you have any questions, you can reach out via my contact information on the screen. Thank you again.